Today we talk about two different topics. One, I want to talk about rate again, because on Friday we had this summary session and there were two questions from your side, and I was a bit unhappy with my answer, so I kept on digging into it since then. It was pretty interesting. So basically it was the question, what's the difference about all these nested rate levels anyway? And yeah, so what do you do when you're unsure about the answer? You Google. I Googled, I read Wikipedia, and I was very unhappy about what I read. It was very fuzzy, the explanations there. Okay, then it's 2024, you ask some large language model. I think I asked ChatGPT or Claude, I don't remember. What's the difference between rate 1.0 and rate 0.1? And the answer was also not satisfying. Because if you look at it, it's really like you swap the middle columns, yeah? So you don't have any difference in terms of redundancy and in performance. Yeah, I mean, you can make an argument, and that's what some of the explanations do, is say, okay, yeah, but you could argue along the lines of the subsystem. So here in this situation, if you have an issue with any of the disks here, let's say this one, yeah, then the subsystem fails because it will only have the odd blocks available if this goes down. Yeah, oops. In contrast, here, if in rate 1.0, yeah, if any of those disks fail, yeah, this subsystem can still serve all the odd blocks because you have a copy inside the subsystem. So that's a different kind of argumentation. It's not arguing along the leaves. It's not saying I have these disks no matter what happens on top, no matter what nesting happens on top, but it's arguing along the lines, what can the subsystem do? Yeah? Not sure. I mean, that really depends on whether you have software, hardware rate, whether you, what are the capabilities of these things, yeah. So you always have to be careful in these discussions to have a very conceptual view. We had so far, arguing along the lines, okay, at the end of the day, what kind of disks are on the leaf level versus, okay, within this nesting tree, what can each internal node do? What are the capabilities? Yeah? So that's one thing to keep in mind. And the other thing you may want to look at is what happens when a system fails. That's another subsystem argument. Maybe we do that to wrap up today. But first I would like to show you something different. So how do you approach such a problem anyway? So that's my idea of today's lecture, is also to show you a little bit how we approach problems. Could be in the context of a bachelor thesis or master's thesis. So you have a problem you're unsure about. In this scenario, what is the performance benefits? What are the error scenarios? What is the resilience of a given nested rate level? So what did I do? I started thinking, and when I think, I write down my thoughts in Python. Python is a thinking tool supporting you in your thought process. Yeah, I cannot recommend it strongly enough. It's so helpful. Yeah, and that's what I want to show you, because I spent the last days hacking stuff. And one important tool in databases is what's called a cost model. So we try to model the properties of something along the lines of a cost model. And that's what I did. And what I would like to show you. Right, so let's... So I will also talk about resilience, but for the moment, okay, so the question is, okay, now I have whatever rate configuration, I have a rate array, how do I model its performance? And I did that by first modeling a class called subsystem. Again, keep in mind, get rid of the idea that we are necessarily handling disks. Yeah, that's a big confusion in these discussions with rate. Yeah, it's always, I also had that on my slide, oh, there's a disk, a hard disk underneath. No. That's not how this works. It's really like there's a subsystem. Yeah? So basically you have some sort of rate level here on the top, whatever, 0, yeah? And then you have a subsystem. That's a black box. Whatever that black box is doing, it doesn't matter. It really doesn't matter for the moment. Yeah? So it could be whatever here's rate level 1, and then there's other subsystems down there. And those leaves, eventually, I will be calling them devices. That's the device. That's the device. And that's the device. Yeah? That could be a rate 1, 0. with 4 disks. Yeah, the first RAID 0 striping stripes all blocks across those subsystems here. This is a subsystem. Again, this is like tree inception in B trees when we talked about that. Yeah. Yeah, this is a tree that has 2 children subsystems. Yeah, each subsystem is a valid RAID array or RAID configuration. This is a RAID 1 with 2 devices. Yeah, so that's the recursive stuff as in B trees. Yeah, and I'm trying to model that. So how do I model that? So the first thing is you need an API. It's abstract. And then what do I want to model? I want to model the read performance. That is sequential read performance I get from such a device. Again, recall read performance, sequential versus random, different thing for many devices. So I keep that apart. So you have sequential read performance, we have sequential write performance, we have the I/O operations per second. So that's the read I/O performance, which means the number of random accesses you can do on such a device. Yeah? On a hard disk, it's 1 disk ARM SSDs, you have multiple threads. That's what you get. Write I/O performance is typically a bit slower for many devices, in particular SSDs. Read and write on a hard disk is more or less the same, but for SSDs it can be a bigger difference. And one method is a storage blow up. So that is how much does this particular subsystem blow up the storage. For instance, if you have 1, this means that this blows up the storage by factor 2. Yeah, so you don't store the data once, but twice, obviously, across those subsystems which happen to be devices. For 0, the storage blow up will be 1.0, meaning nothing happens. So it's a sequence of factors I keep on multiplying in those calculations. Yeah? So this will be 1, this will be 2, and of course depends on the number of subsystems here. So the number of subsystems for RAID 1 determines the blow up. Huh? If you have F subsystems, the blow up will be F. Okay. Yeah, there's also resilience. We'll talk about that in a moment. It's a longer story. For the moment, just look at the performance. Yeah, and then there's a subsystem array. So this is basically a subsystem consisting of a couple of other subsystems. So this has links to subsystems. Yeah, any RAID level we talked about, be it 0, 1, 4, or 5, they have these links. Yeah? So in other words, what I'm showing here in the code is inner nodes in that tree, so to say. Yeah? These things here down there don't have links to other subsystems. Only this has 2 links and this has 2 links in this case. Yeah? So far so clear? Okay. And that's what you're seeing here. That's again abstract. Again marked just to be on the safe side. This is abstract. Yeah. Okay, then we need leaves. So a leaf is a concrete device. Yeah? Again, implementing that API. And here for a device, you want to specify, okay, what are the performance characteristics, now I got it, for this specific device. So you specify all these parameters in the initializer here. See it? You have to look up whatever, that is my device, and from the tech sheet of that device, you will get these numbers in one way or the other. Storage blow up is 1 for this device, which is, okay, if you look inside the device, it's not true. Typically, all of these devices have some sort of blow ups, have some sort of redundancy through error codes, but it doesn't matter for the discussion. Yeah? I will assume that these devices are black boxes. I do not look inside for the not even for the moment. We do not look at it inside at all, for today at least. Yeah, so I don't care about the storage blow up done inside. Huh? So for instance, SSDs do that, do redundant things. I really don't care. Huh? So the storage blow up is 1 in all cases. Yeah, with that, I can model devices. Yeah, and then I can model the different RAID levels. So here, RAID 0, of course, yeah, extends subsystem array. But here I have to specify the different the properties of a RAID 0 array. Yeah, then I'm not sure whether we go through all of them, but basically those properties depend on the properties, the performance properties of what is underneath. Maybe we start with a test that makes it clearer. Where's my tests? So now there's this rate. This is all on main, what I'm showing. So this is now, we had this rate assignment test before. Yeah, which block gets assigned to which disk, yeah, and what is a data block and what's the parity block and stuff like that. Now there's, in addition to that, this rate performance test. Okay, here. And here you see how that works. So basically I specify a device, then I check for the properties, whether they're returned correctly. It's a very stupid test, but anyway, I also write down stupid tests to be on the safe side. And now if you look at a rate level like, I want to start with rate level 1 actually. If you look at rate 1, what I do is, so I specify a device here, yeah, assign it to this variable. I say that's the number of subsystems, it's a parameter. And then I create a rate 1 subsystem. And how do I do that? I say, okay, I have a list. This has an instance and has one entry that is this device. And then there's this nice or weird, no matter however you want to call it, Python syntax allowing me to blow up the list. Yeah, so actually this is a list that has 6 entries, and all of these 6 entries are this def instance. So this is def, comma, def, comma, def, comma, def, comma, def, comma, def. 6 times the same reference to that device. Yeah, that's what I'm doing here. So that's my subsystem. And then I go through the expected performance behavior I'm seeing from such a device, from a rate 1 device. If you go back to our implementation, why is it always closing this file? I don't know. Here we are. If you look at rate 1, for instance, yeah, now we can think about whether that makes sense or not. So here I'm assuming that the performance I'm getting is the sum of the performance over all subsystems. Yeah? So the sum, yeah, of the sequential read performance over all subsystems. Yeah? Assuming that of course, that it also requires that whenever you have a request, you distribute the requests accordingly. But if all of the systems are busy with read requests, with sequential read requests, that's the sum you're getting, basically. Yeah? And then you can do the same for write performance. Okay, there we are in trouble because, yeah, we're replicating across all of these systems. Yeah, again, so we have 1. And we have these subsystems. Yeah, those are subsystems. And now if I write, okay, I have to write to all of them because I'm creating replicas. Yeah? And then I'm blocked by the slowest system. Yes, you write exactly the same data to all of these systems, but here I'm taking the minimum. Yes, the minimum of the write performance over all of these subsystems, which is a good reason to configure your rate 1 device in a way that all of these subsystems have the same write performance. Otherwise, you will be blocked anyway with regards to writes. Yeah? Yeah? Is that clear? Yeah? And so on and so on. For read performance, it's again the sum. That's very similar. So read I/O operations per second is basically, I think in our case, it's more or less the same thing as the sequential read. So you see it's a sum. For write again, you are blocked by the slowest. You have to write to everybody anyway. So if one of the devices is slow, yeah, you have to wait. I'm sorry. Yeah? Because the contract is that when you write a block here in rate 1, it has to be written on all of the subsystems. You cannot just write it to 2 and then wait for the 3rd to eventually write it. Yeah, there are also approaches for doing that. But here we really have to wait that it was written everywhere. And so forth and so forth. Yeah, for rate 0, let's look a bit at those, or should we look at the test again? Maybe we look at the test a bit. Test. Now it's kept open. Yeah. I'll have to test rate. Here we go. Right, so that was test rate 1. Yeah, I have one device with 100 megabytes read and write throughput, 1000 I/O operations per second. Yeah, so basically around 10 milliseconds. 10 milli, no, that would be 100, right? That's actually pretty fast for if it were a hard drive, it would be fast. But I'm not specifying what kind of device. I'm just specifying the numbers, yeah? Just the performance, main performance characteristics. Yeah, then you can see what you get here. So I assure here, for instance, the read performance is whatever is the base performance times the number of subsystems. Write performance is 100, no matter how many subsystems I have. Yeah, all of my subsystems here have the same performance. Read I/O performance, again, number of subsystems times 1000. Same for write performance, just this 1000, yeah, because all have the same performance, so that's perfect, balancing, and that's the result, and so forth, and so forth. Yeah? And the storage blow up, of course, is number of subsystems. Yeah? If it were rate 0, it would be 1, but this is rate 1, so it must be, that's 3 replicas, so it's times 3, the storage. Rate 0 is very similar to that. So here I create a rate 0, again with 6 subsystems. Sequential read performance is number of subsystems times 100, yeah, because you can read, if you read a large file, you read one chunk from that device, the other chunk from that, and so forth and so forth. Sequential write performance is much better here, yeah, because you don't have to write replicas. Yeah, you just split the file, split your request, and then distribute it over the different subsystems, and yeah, in an ideal world, in the optimal case, that is what you get. So number of subsystems times 100. And the same holds for the random I/O operations. Blow up is 1. You also see in the tests, that's something we didn't discuss last time, is when you misconfigure your devices, what happens. So in this scenario, I use the rate 0 with misconfigured heterogeneous devices. So I have 2 devices. One is double the performance. So this has only 100 megabytes per second. This is 200. So everything here is times 2 on the second device. Yeah, and then I can create a rate 0 with that. Yeah, you can say, okay, the device type 1 and the device type 2, only 2 devices. So here we are. What did I say? This is 1. This is D1 and D2. And D1 is 100 or 1000, whatever. 100/1000. And this is 200/2000. Okay? So now, what is the performance? What is the sequential read performance? Is actually the minimum performance of a single subsystem times 2. Yeah, if you have this round-robin assignment of blocks, yeah, you will always be waiting on this guy. Yeah, so it doesn't help you that you have this fast device here in the array. Yeah, what you get is whatever the minimum is of the array times 2, times number of subsystems in this case, in all cases, yeah, in the general case. So, but we have 2 subsystems. Yeah. Same for the write performance. Yeah. It doesn't help that this is twice as fast. Yeah. Same for I/O performance. Get read I/O performance. I know here it's a sum actually. Yeah. If you here you can spread it out. If you spread out your requests accordingly, then you can do that. So that means that you get double the amount of requests here compared to there. Then it still works, and the same for the write performance. And what you could do to compensate for that is, and that's what we didn't discuss so far, is that you nest rate levels to fix this problem. Yeah, so if you have a storage system that has devices of different type, what you could do here, and that is what this test is doing. So maybe let's write down the tree. So there's one rate 0, yeah, and then there's another rate 0, which has devices of type 1. So we have here D1, D1, D1. It's getting a bit D1. Okay, and here's another 0. And this has D2 and D2. Okay? That's basically what I'm doing here. Device type 1 is 100 megabytes per second, device type 2 is 200, and then I say I create the subsystem, I have 4 of type 1, I still have these old disks hanging around, I want to use them in my data center, but the boss acquired 2 super fancy new disks, so let's use them some way. In some way, what do? I put them into subarrays, I create another nesting level on top with RAID 0, this one, yeah. And now what is the read performance I'm getting? If you think about that, okay, here read performance, 2 times Z is 400, 4 times Z is 400. Yeah, like that you can balance and yeah, you can use different types of devices in the same array and still balance out the performance. Yeah, is that clear? Yeah, kind of, okay. Yeah, that's basically what this test is showing, and then you can do the same tricks with RAID 1 configurations. Yeah? What if it's misconfigured? What is the performance you're getting? What if it's well configured? Again, balancing out for the different RAID levels. Yeah? So I invite you really to look through these tests. I found that really, and again, showing you how we approach these problems. Yeah, really when writing the tests. Yeah, so you step through these things through debugger and see what you're getting with these methods, and then okay, you get a number, and then you check it. Or does it make sense? Yeah, you scribble it on some paper. Yeah. Okay, that makes sense. For some methods, you get no, that doesn't make sense at all. Yeah, or I believe it makes sense at all. Then you give it to a review to a PhD student, and the PhD student says, no, this doesn't make sense, Jens. You should fix it. Or then we fix it. Yeah, that's how it works. Yeah, so you really have to not blindly carve in stone what you get, but really think about the results. There's always 2 calculations. There's always 2 ways of calculating the same result, and let's hope the 2 results match. That's what we did here. Yeah. Right. Yeah. Then you play the same game for RAID 5. So for RAID 5, the calculation is always read performance is number of subsystems minus 1 times 100. Why is that? Because, of course, in a RAID 5 system, yeah, if you have whatever, let's make it, well, let's make 3 is enough, so we need at least 3 subsystems. Yeah, these block assignments, so if it's block 0, now we started with 1, 2, and that's parity and so forth. So in each of these rows, you lose one of the blocks, which means the read performance you get when you use all of the subsystems to their maximum is always number of subsystems minus 1, because you have this parity which doesn't help you anything in that regard. Yeah? So basically the read performance is the sum of the subsystems. So it's the number of subsystems minus 1 times 100 if it's an even distribution of performance of the devices. Yeah? And that basically explains this number. And you also see that when you look at, how this is calculated in the code. Yeah, we also factor in, have to be careful, same problem as with the other RAID 0 and 1 levels. You have to be careful to think about, is it really the sum, is it the minimum? So the test I just showed you, all devices have the same performance, so this problem doesn't occur. In reality, devices may have different performance, so you're blocked by the slowest device. Yeah? This may happen. Okay. Right. Yeah. Yeah, then we also have tests for these nested RAID levels 0, 1 and 1, 0. So I invite you to take a look at that. So played here also with different number of disks, and different configurations. Here it's 2 inside and 3 outside. Here it's 3 and 2 and so forth and so forth. RAID 5.5. That's also interesting to think about. This case here, so we also use scaling here. So here we broke it down again to only factor 2, but basically, yeah, of course, if you have 5, then you would end up in something like this. At least 9 subsystems on the leaf level. Yeah, makes a lot of sense. And that also brings you very quickly into the discussion, okay, and we had that discussion before. I mean, what can fail anyway here in such a scenario? Yeah, what can fail in that scenario? And yeah, of course, any of those subsystems may fail from the point of view of this guy. If this fails, it's okay, but not more than one. Any of those subsystems may fail. And yeah, the other thing to what may happen is, of course, what makes such a subsystem fail? Any of those leaf-level subsystems failing. Yeah, so there are different scenarios, different resilience scenarios. Resilience scenarios, meaning, so given a particular configuration of your RAID systems, what is the type of error scenarios you can survive? What may happen? What may go wrong in the system and you're still up and running? And that's what I want to automatically compute. And then we will do that in a moment. Huh? Right. We should execute the test. Is that still in the print? So I commented it in the code. Yeah. Okay, so here, and that's basically, if you remove this command here, you will see that in the tests. What is the configuration I'm using? Oh yeah, maybe we draw that on the blackboard. I think I should change this. It's a leftover. So it's a 5.0. Do we have a 5.5 resilience? I would like to start with that one. No, we don't have it. Okay, so let's do that one, whatever. So 5.1.0, or starting from the top, it's 0.1, 0, and how many? Everything is times 3, yeah? 0, 1, right? 0, 1, 5, everything times 3. 0, 1, 5, and so forth. Yeah, don't spell it all out. Tra la la la. Yeah, and then what is the error scenarios? And that's basically what this enumeration is giving you. So now if you look at the output, you see the cases this configuration may survive. And this is sent to the output along the nesting of the tree. So you see an indent here, and that indent means that, okay, that is the second level already, because on this level, if any of the subsystem fails, you're screwed, yeah? Because 0 doesn't introduce any redundancy. Yeah? If you have at the top level any of the subsystems failing, you're screwed, so there's nothing to say about resilience here. Any 0 RAID node doesn't help with respect to resilience, only with respect to performance. Yeah? That's why there's no output. But here, on the next level, you see there's 3 outputs for RAID 1. And this says, yeah, all but one subsystem may fail. Yeah? So basically, we have the local view on this specific RAID node now. Yeah? So we're looking from the point of view of this one. What can I survive? Well, I can survive all but one. Yeah? If there's at least one subsystem available, everything is fine. I still have the data. That is what RAID 1 is about. And that happens for all of these entries on this level. Again, in the tests, you will see that for each of those levels in the nesting, I use the same RAID level. Do I have to do that? I don't. Do I want to compute even more? No, I don't. So let's keep it for the same level, the same rate level on each level of this tree. Yeah? But this could be in theory 1, 5, 27, whatever. Yeah? But of course, if now I have 3 nodes. Each of the nodes has the same property. Yeah? And that's what you see here. And then again, if you go down to the nesting, you see, aha, for such a rate 5 node here, any of the subsystems may fail. That's okay, but just one. Yeah? Other than that, you're not resilient anymore. And that's basically what you get when you make this print out. Yeah? So that's what I wanted to show here. Yeah, and then we had some discussion in Slack, actually discussing what will be the next assignment, and I was joking, okay, let's ask the students what is the properties of rate levels 500, 5105. Just made up these numbers, and then I said, oh wait, actually with implementation it's relatively easy to do, yeah, and now also for you, this is on main, because you just have to write down the nesting, who cares, right? I mean, that's basically what I did here, and this is insane, yeah, if you think about that. This is, yeah, if you start, again, this is bottom up. So I start with the first digit here. This is a 5, you see here. This is the top-down definition. I have this device, and I have it 3 times here. And then I nest that into a rate 0, so I already have 9. It's always times 3, times 3, times 3, times 3, times 3, times 3. Yeah, and then I check the performance numbers. And here, I have only one test here to check the read performance. And now what I'm doing here is, and I found that very insightful, is basically I do the second kind of calculation. So the first calculation is done here recursively inside my implementation, but then I do the other implementation basically on a piece of paper or here in the unit test and say, okay, if I start from the bottom and now I have a rate 5, what do I get in read performance? Yeah, number of subsystems minus 1. That's the multiplication factor. That's the performance blow up, if you want. Yeah, that's happening at this point. What do you get for rate 0? Yeah, number of subsystems, yeah, multiplied to what I had before. Another rate 0, number of subsystems. It's always the same for each level, so this is easier. Of course, it would be the number for the blow up and the fan in for each level then. Yeah? But here it's always 3. Or this constant, so it's easy. Yeah? And again, there's a rate 5, so it's minus 1, rate 1, same thing, and so forth, and then you get the same number, actually. Yeah, and you can actually, if you are really bored over the Christmas holidays, you can check through all these scenarios that may happen in such a rate configuration, and it's still not failing. Yeah? Yeah, of course, you will never see a rate 0 here because rate 0 is not resilient to anything. Yeah, but that's important. Really, the takeaway message is, I think in all of these discussions, there is this huge confusion thinking about the leaf level, which disk configurations may fail. Yeah, okay, this may fail and tra-la-la-la-la. Yeah, I think it's a hierarchical problem. So you really have to worry about, okay, at that level, what may fail? At that level, what may fail? Yeah? And at the leaf level, but also the internal node level. And then you have the failure scenarios. And then comes the second thing. Then you can think about, okay, what is the maximum number of disks or the maximum number of leaves that may fail to survive a failure? And how should they be distributed? Because it could be that for 3 disks, if they, yeah, I mean, do we have an example?